Hi, I'm Vered, and today I will be talking about a bookworm barely graduating from the University of Life on language models and common sense knowledge. In the last 3 years, NLP is almost synonymous with language models. And so there are different types of language models which are used both as a representation layer and for text generation. And throughout this talk, I will use BERT as the canonical example for math language model, although some of the papers I will mention actually use different models in practice. So language models are pre-trained to read a large text corpus such as Wikipedia or the web. And as a result, they learn about syntax, word meanings, and factual knowledge. And they have been shown to contain a lot of factual knowledge. And here's one example. And they may be used as to complete facts in knowledge bases. Here's one example. BERT knows that the native language of Mamuti is Malayalam, which is a very specific fact. And you can see by the fact that I'm not sure how to pronounce these words that I didn't know this fact before I was preparing this talk. And most people in the world probably don't know it. At the same time, language models sometimes lack very basic common sense knowledge and reasoning abilities. For example, when I tell BERT, I spilled coffee on my laptop and now I need to buy then BERT says new car. Common sense is a bit difficult to define, but I'll go with the working definition from our ACL tutorial last year. So that is the basic level of practical knowledge and reasoning concerning everyday situations and events that are commonly shared among most people. So this includes, for example, physical common sense, such as knowing that it's a bad idea to put your hand on top of a hot stove. Social common sense, such as knowing that commenting on someone's weight is impolite. Temporal common sense about typical times and durations of events, and more. Why do NLP models need common sense? Mostly because we want them to be able to behave reasonably when they encounter situations that are outside of their training data sample. For example, a translation system sometimes needs to translate implicit meaning in the source language explicitly to the target language, such as in this case, translating grass-fed yogurt to the equivalent of yogurt made of milk from grass-fed cows. And you can see here that Google Translate incorrectly translated it to Hebrew to the equivalent of yogurt with grass. In reading comprehension, if we come across a headline such as this, Stevie Wonder announces he'll be having kidney surgery during London concert, then this headline has multiple interpretations, but our common sense knowledge and reasoning abilities would eliminate the interpretation that Stevie Wonder performed during his own surgery. And perhaps more importantly, if we use models such as GPT-3 as basis of medical chatbots, then we want them to have social norms and ethics, and so that they don't end up advising patients to kill themselves. So in this talk, I will start by talking about the kind of common sense knowledge that pre-trained language models have, and some examples of how to extract and use this knowledge. And I will then discuss the limitations of using language models as a source of knowledge. And finally, we will talk about one possible solution to that, which is to incorporate external knowledge into language models. So let's start with extracting common sense knowledge from pre-trained language models. First, I want to discuss the appeal in extracting common sense knowledge from language models. And so let's say that our fundamental goal is to teach machines common sense, and our intermediate goal is to have some kind of a machine-readable resource of such knowledge for models for downstream tasks to consult with. So in the past, it was common to either collect this knowledge from people or extract it automatically from text. So the first approach is not very scalable because it's impossible to manually enumerate all the common sense knowledge in the world, and it's very costly and time-consuming to try that. The second approach works, but suffers from reporting bias. That is, people tend to speak more about the exceptional than about the obvious, because it's obvious for everyone. And this is reflected in text corpora. And so by looking at corpus frequencies, you might learn, for example, that people murder more than they breathe, just because it's more newsworthy. And so recently, the alternative of extracting such knowledge from pre-trained language models has become popular. And indeed, language models capture a lot of knowledge, including facts that are not even explicitly mentioned as is in the training corpus, because these models can aggregate across different contexts. And these models have been used successfully to complete common sense knowledge bases. They're also quite good at associating concepts such as bear with their properties such as has clause. In some tasks, we need to employ implicit common sense to get to the correct answer. Let's take this example sentence. Children need to eat more vegetables because they are healthy. Syntactically, the word they can refer either to children or vegetables. And we as humans very easily resolve this reference by employing knowledge that is implicit in this context. So, for example, that vegetables are healthy, that eating vegetables can make you healthier, and that people generally want to be healthy. And then we can correctly predict that they refers to vegetables. Inspired by discovery learning in education, we can view this as a process of self-asking questions and answering them. So we have this human learner, and they might self-ask a question such as, what are the properties of vegetables? And then answer it with their existing knowledge that, for example, vegetables are full of vitamins, they can make you healthier, and etc. And then using this knowledge, the learner can discover new facts, such that in this context, the word they refers to vegetables. Last year in EMNLP, we had a paper in which we proposed the self-talk paradigm, in which we replaced the human learner with a neural language model. And obviously, a language model is not as good as humans on this task, but still. And so the goal is to solve question answering tasks, specifically those pertaining to or requiring common sense knowledge. And the means is this nested QA component. The input to the self-talk model is a multiple choice instance. So that consists of a context, such as children need to eat more vegetables because they are healthy, and a set of answer choices, children and vegetables. And the goal is to predict the correct answer choice. The model consists of a knowledge discovery component as well as a question answering component. The knowledge discovery component takes the context and concatenates a prefix of an information-seeking question, such as, what is the purpose of? The language model is then used to generate the ending of that question. So overall, we get the nested question, what is the purpose of vegetables? Assigning the ending into the corresponding answer prefix template, we get the purpose of vegetables is, and again, we'll let the language model generate the ending. So finally, we get the nested answer. The purpose of vegetables is to provide a good base of nutrients and energy. And we repeat this process multiple times, so we get multiple nested answers. So the output of the knowledge discovery step is a list of nested answers, and they are then used by the question answering component. The question answering component creates a statement from each combination of the context with an answer choice and a nested answer. And we would like to predict the answer choice corresponding to the most plausible statement. But we don't really have a way to measure plausibility. So instead, we use a standard proxy, which is language model score. Specifically, this is computed in a pretty standard way by inputting the statements to the language model and then predicting the conditional probability of each word given the previous words. Then taking the negative average log of the product of probabilities, we get cross entropy loss. So the lower the loss is, the more likely the statement is considered by the model. Language model score is not a perfect proxy, and we will get back to it soon. So the question answering component predicts the answer choice corresponding to the statement with the lowest cross entropy loss. And this is the overview of the self-talk model. We evaluated the model on 6 multiple choice question answering tasks pertaining to different types of common sense knowledge. So for example, we use the social IQA datasets to evaluate the model on social common sense about people's goals and mental states. For example, although Aubrey was older and stronger, they lost to Alex in arm wrestling. How would Alex feel as a result? 1, that they need to practice more, 2, ashamed, or 3, boastful. And the correct answer is 3, boastful. We also evaluated the model on typical causes and effects using the COPA dataset. So for example, the man broke his toe. What was the cause? Either he got a hole in his sock or he dropped a hammer on his foot. And the correct answer is the second. We also evaluated the model on physical, temporal, and general common sense knowledge. As baselines, our first baseline is simply the ablation of the nested QA component. So we just want to know whether additional knowledge helps. And so we score the answer choices based on the plausibility of the context with the answer choice. We also have several baselines that use expert knowledge from external knowledge sources instead of generating this knowledge from a language model. So for example, we can use ConceptNet, which is a common sense knowledge base, to obtain knowledge such as vegetables are required for eating vegetables, and eating vegetables is motivated by being healthy. We can also extract directly from a text corpus facts such as vegetables are healthy. And finally, we use Comet, which is a model trained on the atomic knowledge base. Comet can reason about people's mental states. So here it tells us that the cause for the context is that children wanted to live longer. What you see here is the average accuracy across the 6 tasks. And the takeaways are that, first of all, self-talk performs better than the baselines with no nested QA. So that means that knowledge helps. The second thing is that the model performs similarly to models with expert knowledge or external knowledge. But in both cases, the performance is still far from human performance as well as from supervised performance. So there's plenty of room for improvement. And specifically, one of the challenge is to get the model to know what knowledge is missing and ask specifically about that, or what knowledge would especially be helpful to answer the question. Okay, moving on to limitations in relying on language models as a source of common sense knowledge. So first of all is our models. They're not human curated resources. So when we use them, we automatically compromise precision. That's pretty much a given. Specifically, language models have been shown to be insensitive to negation. So they also score the negated version of a fact pretty highly, such as birds can't fly. Similarly, because of their distributional training objective, they tend to confuse similar but mutually exclusive concepts. So here's an example. This is from the Jiang et al. Last year. And so they asked BERT who DirectX is developed by, and you can see that BERT predicts several names of companies with pretty similar scoring. And they also suggested one way to overcome this problem by paraphrasing the prompt multiple times and then aggregating the predictions from the different for the different prompts. Finally, language models don't really differentiate constant facts such as zebras are black and white from contingent facts such as the color of my shirt, which is incidentally also black. The second problem is that, as I've mentioned earlier, we don't really have a good way to measure plausibility in zero-shot models. Let's look at this example question. A human wants to submerge himself in water. What should he use? A, coffee cup, B, whirlpool bath, C, cup, or D, bottle? The correct answer should be B, whirlpool bath. The standard proxy would be to compute the probability of each answer conditioned on the question, and then predict the answer with the highest language model probability. And one of the problems in doing that, and you can see here that this is identical to the way that I computed it for self-talk. One of the problems in that is that standard language model probability confounds two other factors. One of them is the string length. So generally shorter sentences would be more plausible. And the second is word frequency. So sentences containing more frequent words would be more plausible. Putting aside the differences between word count and subword count, when we normalize by length, we pretty much remove the first confounder. So we will focus on the second. So the problem is that language model probability is distributed across the entire vocabulary, not just the constrained space of candidate answers, which is coffee cup, whirlpool, bath, cup, and puddle. So the different strings representing the same concept, such as whirlpool, bath, bathtub, and bathtub, are competing on their probabilities, and this would favor concepts that either have fewer surface forms or candidate answers with a more common surface form of a concept, regardless of whether that's a correct answer or not. One thing to add here is that there's this subtle distinction here of whether we're talking about different correct answers or different phrasing of the same correct answer. And this argument holds in both cases either way. In a recent paper led by Ari Holtzman and Peter West, we suggest to use a new score that we call domain conditional PMI. So in this score, we normalize the answer probability with some prior probability for the answer given some generic domain prefix. So for example, using a prefix such as the answer is, or if we know more about the task, we can tailor the prefix specifically to the task. And so what this score measures is how much more likely the answer becomes given a question within the specific domain. And we tested this score on many multiple choice tasks, and it pretty much consistently outperformed the other zero-shot scoring methods with both GPT-2 and GPT-3. And we really hope that this very simple method will become the standard for zero-shot scoring, because right now there is not really much standard on how to compute language model score. Moving on to another limitation. Language models actually lack coverage on some domains. It's kind of hard to believe that because you can generate whatever you want with them. But specifically, it has been shown that physical properties of the world and perceptual knowledge are not the strongest sides of language models because they have been trained on text, and these kind of facts about the world are not typically described in text. So in general, rather than learning common sense knowledge only from text, it is beneficial to learn it from additional modalities such as images and videos. And those modalities provide complementary knowledge that is sometimes unlikely to be described in text. Here's an example. If we look across enough class photos, we might learn that the kids in the front row are typically sitting, but those in the last row might be standing. This leads me to the next limitation, which I mentioned earlier in the context of extracting knowledge from text. But I want to stress that language models don't completely overcome reporting bias. So on the one hand, they do assign non-zero probability for very trivial facts that might not be mentioned often or very frequently as is in the corpus. That's because they are capable of aggregating across different contexts, and that's really great. At the same time, they also tend to overestimate rare actions. Here's an example. BERT is trained primarily on Wikipedia, and so it really overestimates the likelihood of dying. And I want to maybe elaborate on that because the likelihood of everyone of dying eventually is 100%. But when we ask BERT what people do most of the time, then we want it to assign a higher probability for things that happen all the time, like breathing and talking, as opposed to something that happens once in a lifetime, which is dying. And the reason this happens is pretty simple. It's because it's trained on Wikipedia, and Wikipedia contains all these articles about very influential people, which are often already dead. And this also happens with estimating rare outcomes. And here's an example from GPT-2, which is a pretty representative example. Given a prefix such as the man turned on the faucet, as a result, GPT-2 predicts the man's blood was spread everywhere. This is not a one-off. This is something that happens once in a few times that you generate text with GPT-2. Another aspect of reporting bias is that language models learn facts about specific named entities, which are very prominent in the corpus, and then they memorize these facts and use them even when they're uncalled for. For example, if you give GPT-2 the prefix Richard has a bad, then it generates habit of saying things that are not true. And if you look at the attention weights, you can see that most of the attention goes to the word bad, which is very reasonable for this very short prefix. But once you replace Richard by Donald, now you get reputation for being a racist. And if you look at the attention weights, you can see that GPT-2 assigns equal attention to Donald and bad. And this is an undesirable behavior for most applications. Finally, it has been shown recently that language models also memorize and repeat private information such as phone numbers. And as is really nicely summarized in this tweet from Tal Linzen, this is not surprising because the training objective of language models doesn't differentiate between what is good or bad knowledge for the model to learn. So learning from additional modalities is a good idea, but we will have to be aware of other types of reporting biases. For example, if we learn from movies, we might learn the undesirable fact that people typically hang up the phone without saying goodbye. Finally, let's talk about incorporating external knowledge into language models, which is some way to overcome these issues. So going back to our children and vegetables example, if we just use an off-the-shelf BERT model and tries to solve this, then obviously BERT would try to predict everything from its vocabulary, and it's not constrained to the two options, which are children and vegetables. And then the vast majority of the probability distribution goes to the word they, which is really syntactically the most common word you use in this context. But it's not informative for our for resolving this reference. And then if we only look at the predictions that are from the constrained set of answer candidates, children and vegetables, we can see that children is the next best prediction, while vegetables is not here even in the top 5. And so this is obviously wrong. In that case, it would help us to retrieve knowledge from ConceptNet, for example. So we will represent the context with some vector representation, and we will also retrieve knowledge, relevant knowledge from ConceptNet. For example, that vegetables are required for eating vegetables, which are motivated by being healthy. So these kind of neurosymbolic models, they consist of the symbolic knowledge as well as some model vector representation for the context. And they typically consist of several components. One of them is the knowledge resource that is being used. So typically you would use you would retrieve factual knowledge from Wikidata or Wikipedia, lexical knowledge from WordNet, and Commonsense knowledge from ConceptNet, Atomic, and Comet. But of course, there are many examples of different resources that are used by models. The neural component is the less interesting part, in my opinion, because typically you would just use the shiny new model. So as I wrote here, you can just use your favorite language model here. And I think the most interesting part is the combination method. And I'm going to show two example approaches, but there are many others. So a very common way is to embed the symbolic knowledge, taking a subgraph from some knowledge graph, and then learning graph embeddings for that, and then taking the graph vector as well as the text vector, concatenating them and feeding them as input to the model. And then the model can choose what to take from each of them. And also, of course, if you have multiple layers or retention mechanism, then it could somehow combine the different information sources. An example for such a model would be the Cagnet model. An alternative approach is to have a main task that is purely neural. You can see here that this context is being encoded into a vector and then fed into a classifier to predict the answer. But then you would train it in a multitask setup with auxiliary tasks that will be supervised by the knowledge base. So, for example, taking the two important words here, maybe, which are healthy and vegetables, you can also have tasks that ask whether and how these two words are related in ConceptNet and train it with knowledge from ConceptNet. And the way that these auxiliary tasks help improve the main task is typically by some kind of shared representation. So, for example, if you use BERT and you fine-tune it for both predicting the auxiliary tasks as well as the main task, then the main task can benefit from this knowledge that is instilled from the auxiliary through the auxiliary tasks from ConceptNet. And an example for that would be this paper from 2 years ago, incorporating relation knowledge into Commonsense reading comprehension with multitask learning. Let's talk about a specific use case that we worked on recently, which is incorporating knowledge into natural language inference models. And let's look at this training example. The office, so the premise is the office is located in Baytown. The hypothesis is the office is located in Texas, and the label is entailment. And so if we train a model on such training examples, then we expect it to learn two things. One of them is that is the fact that Baytown is located in Texas. And the other one is the kind of entailment rules. So for example, it might learn that typically a city entails the state it is located in upward monotone sentences, which would be most of those sentences in the NLI, modern NLI data sets. And while the rules can be learned given enough data, it is impossible and also very inefficient to teach an NLI model every fact it might need. Or if you look at it from the other direction, to expect a data set to contain, to expect the model to learn all these factual knowledge only from the data set it was trained on. And so the solution is to allow the model access to an external knowledge base with these facts. So basically just providing the facts as inputs. And then the model only needs to learn the rules, and that's much more reasonable to expect the model to do. So the question is, how do we incorporate relational knowledge into an NLI model? One way to do that would be to use a model like NoBERT. So NoBERT was trained to incorporate knowledge from Wikipedia and WordNet about entities. And the example that you see here is I copied the figure from the NoBERT paper, but I just replaced the text with the example that I showed in one of the previous slides. So here, for example, you can see that NoBERT will learn knowledge about the entities in the sentence, which would be matched to various different entries in Wikipedia about Baytown and about Texas. NoBERT was tested on entity-centric tasks, so and it improved performance upon a standard language model. Unfortunately, in our scenario, it's suboptimal. First of all, because it must learn everything about the entities in advance. So let's say that we now want to apply the model to the trained model to new entities, and take, for example, this Nanhui, I hope I'm pronouncing it correctly. This is a new city in China that was established in 2020. And then the model that was trained in 2019 has no knowledge about it. And if we want to add this knowledge, that will require fine-tuning BERT again on all the entities, which is quite computationally expensive. And apart from that, it's also memory expensive because the model needs to store all the entity embeddings in memory. So that's quite heavy. So our solution, which is in a recent paper, which is not yet publicly available by Ohadro Zen, is to embed the relations instead of embedding the entities. So for example, now when we look at the same example of the office located in Baytown and the office is located in Texas, then we embed each one of the premises, each one of the premise and hypothesis with this additional vector that contains in the relevant index of the target word, such as the almost last word in each one of these sentences, which corresponds to Baytown in Texas. We're going to embed either the tail vector or the head vector of the located in relationship. So now the model needs to learn the rules as well as these few relation embeddings. So if you have one relation embedding, if you have one relation, it's going to have to learn two embeddings, one for the tail and one for the head. And if we just have a handful, it's still going to be just a few vectors to learn. So given a small number of training examples for a given relation type, the model manages to learn it separately from the facts. And it outperforms the baselines on NLI challenge sets. It also succeeds in predicting instances with facts pertaining to entities that are not seen during training. And it is much less computationally expensive, much more efficient, both in training time, because now we only need to train it on a few hundred examples. As you can see here, this relation was learned with about 700 examples. And also in memory, because we don't embed the entities, we only embed a small number of relations. The main limitation is that it is less generic than NoBERT because it is designed for a specific type of tasks that pertain to two sentences. So what are the limitations in general of incorporating external knowledge into models? So first, knowledge graphs have limited coverage because, as I've mentioned, it is impossible to manually enumerate all common sense knowledge. Second, inferences may be incorrect in certain contexts. At the basic level, we have polysemy, because sometimes a word has multiple senses and it's not always captured in the knowledge graph. So for example, if you look at ConceptNet, the entry for mouse has location of. So it says that on the one hand, a mouse could be located in a hole, which obviously refers to the animal sense of mouse. But on the other side, it also says that it could be located on your desk, which hopefully refers to the computer device. And so you need to be able, if you use it, you need to be able to differentiate which facts determine which facts pertain to which sense, and also determine the correct sense of the word in the given sentence. Also, it also happens in like a broader sense of context. So for example, given a sentence such as Bob found the cat on the street and adopted it, if you retrieve the most similar atomic node for this sentence, that you would predict incorrectly that Bob needs to first go to a shelter, which it is incorrect because Bob found the cat on the street, not in a shelter. But if you use Comet, which is trained on atomic, but models or encodes the specific context and tries to predict the most relevant inferences for a given context, then it correctly predicts that he needs to go to the street. To recap, language models capture plenty of common sense knowledge, but they often lack in reasoning abilities. And yes, that includes even GPT-3. And I'm going to use this example. The prompt is, the girl spilled orange juice on herself and started crying. Why are you crying? Her dad asked. Because my clothes are wet, replied the girl. And why are they wet? And let's see what GPT-3 says. Because I fell in the swimming pool. And why did you fall in the swimming pool? Because I couldn't see the water, the girl replied. The moral of the story is, always wear a blindfold when you go swimming. I don't think I need to add anything after this example. So knowledge from language models, use it at your own risk. And you need to know that sometimes these models overgeneralize, generate nonsense, and suffer from reporting bias. For this reason, some tasks can benefit from incorporating knowledge from external resources. Thank you for listening, and I really hope to see you in the Q&A session, and you're also welcome to email me if you have any questions. I'll also use this opportunity to say that I will be looking for students. So if you're interested in working on semantics and common sense reasoning, consider applying to UBC and working with me. Thank you.